When designing a SmartNIC or DPU, one needs to engineer it for the worst case, as eventually a customer will push your product to the theoretical limits, even if only in their lab. Taking a pat on the back from a customer when your product outperforms their expectation is always better than the alternative. Conventional CPUs, like ARM and even GPUs for that matter, follow the classic 1945 von Neumann architecture shown here. In this model, the CPU or GPU fetches its next instruction from memory. If necessary, it brings the data it needs to operate on in from memory and pushes the calculation back to memory. This architecture makes overall solution performance entirely dependent on memory performance, and this is known as the von Neumann Bottleneck. Over the past 75 years, many innovations have come along, like caching, predictive algorithms to drive instruction and data prefetching, and pipelined execution to reduce the impact of memory accesses. Unfortunately, this architectural flaw still exists. SmartNICs or DPUs should be capable of acting on all input and output traffic. So a dual-port 100G NIC translates to 400 gigabits per second of traffic, or 50 gigabytes per second. Ideally, there are dedicated direct memory access or DMA logic blocks for writing this to and from system memory, and another dedicated block of logic to read and write network packets to this DPU memory for the network packet interfaces. One of the best examples of von Neumann SmartNIC is the NVIDIA Bluefield 2 DPU. Here we have an 8-core ARM-based DPU using DDR4 memory. The Bluefield 2 team at Mellanox pulled out the older M-pipe logic from Tylera and replaced it with their highly performant proven ConnectX-6 logic. The Bluefield 2 uses DDR4 memory at a speed of 3,200 million transfers per second, with each transfer being 8 bytes. This system can ideally transfer 25.6 gigabytes per second. So we have a network bandwidth demand access requirement of 50 gigabytes per second that exceeds the available ideal memory bandwidth of 25.6 gigabytes per second, which means it's oversubscribed by a factor of 2. And this is before we consider that there are at least 10 devices, 8 of which are ARM cores, the ConnectX-6 engine, and a DMA engine, all competing for access to this bus. Additionally, there are several other logic blocks also doing various crypto operations, also competing for access to this memory. So this factor of 2 oversubscription only grows, hence the von Neumann bottleneck. Several tricks can bring this down, but for the von Neumann architected systems, this bottleneck is very real. Hopefully this clarifies why using ARM cores for data plane processing of network packets can be challenging. Also, we've not even looked into the mismatch between the 100G packet rate, CPU speed, and core counts. We'll save that for the future. Thank you for your time.